Welcome to our journey through the wonders of our solar system. Tonight, we'll explore the fascinating worlds that orbit our Sun, uncovering incredible facts and stories that make each planet and dwarf planet truly unique. From the fiery surface of Venus to the icy edges of Pluto, this 4-hour journey is designed to calm your mind, spark your curiosity, and gently guide you into a restful sleep. Sit back, relax, and let the mysteries of space lull you into a peaceful slumber. The cosmos is calling. Let's answer by diving into its endless beauty. If you find this video helpful, please give us a subscribe. A small compliment from you is a huge motivation for us. Venus, Earth's so-called twin, is one of the most enigmatic worlds in our solar system. Beneath its dense, sulfuric clouds lies a realm of extremes, where temperatures soar to 900 degrees Fahrenheit, 475 degrees Celsius, and atmospheric pressure crushes with the force of 90 Earth atmospheres. Once considered a possible Eden-like counterpart to Earth, Venus now appears as an infernal wasteland, a place where lead melts like wax, and the glow of rocks in the dark speaks of unbearable heat. How did these two planets, so similar in size and composition, diverge so dramatically over billions of years? The answer remains one of the greatest mysteries in planetary science. The story of Venus's transformation is one of both science and exploration. For centuries, the planet's surface remained veiled behind its perpetual cloud cover. Early astronomers believed Venus might be hot and humid, a tropical greenhouse teeming with life. In the 1950s and 60s, many even imagined it as a world resembling the lush wetlands of Miami, Florida. These visions were shattered in the late 20th century, when the Soviet Union's Venera probes revealed an entirely different reality. Instead of a verdant paradise, Venus was a barren desert with no water, a surface scorched by heat and battered by acid rain. Venus and Earth share much in common. Both are rocky planets, formed from the same primordial cloud of gas and dust over 4 billion years ago. Their similar sizes and compositions earned Venus the moniker of Earth's twin. But Venus diverged drastically due to its thick, carbon dioxide-dominated atmosphere. This potent greenhouse gas traps solar heat with relentless efficiency, turning the planet into a furnace. Unlike Earth, where carbon dioxide levels are measured in parts per million, Venus's atmosphere is almost entirely carbon dioxide, making it a case study in what happens when the greenhouse effect spirals out of control. While Earth's atmosphere supports life and moderates temperatures, Venus's acts as a heat-trapping blanket. The result? Surface temperatures that exceed those of Mercury, the closest planet to the Sun. The lack of water further exacerbates the situation. On Earth, water acts as a buffer, absorbing carbon dioxide and regulating the climate. Venus, however, lost its water long ago, possibly due to the Sun's intense radiation. With no oceans to stabilize its climate, the planet's runaway greenhouse effect took over, creating the hellish conditions we observe today. In 2005, humanity took a bold step toward understanding Venus's transformation with the launch of the Venus Express spacecraft. Built by the European Space Agency, ESA, and launched aboard a Russian rocket from Kazakhstan, the spacecraft embarked on a 250 million-mile journey to Venus. Its mission was clear: to study the planet's atmosphere, surface, and climate, to uncover why it evolved so differently from Earth. Arriving in April 2006, Venus Express faced a perilous task. To enter orbit, it had to slow down by 3,000 miles per hour, using a series of precise engine burns. During this critical phase, the spacecraft disappeared behind Venus, leaving scientists on Earth in tense silence. After 10 agonizing minutes, a signal confirmed success. Venus Express was safely in orbit, ready to begin its groundbreaking mission. The spacecraft's polar orbit allowed it to sweep over the planet's poles, dipping as close as 155 miles from the surface, while climbing as high as 40,000 miles. This vantage point provided scientists with an unprecedented view of Venus's thick atmosphere and rugged surface. Equipped with state-of-the-art infrared instruments, Venus Express was designed to peer through the planet's dense clouds and reveal details invisible to earlier missions. Infrared technology became the key to unlocking Venus's secrets. Unlike visible light, which scatters in Venus's dense clouds, infrared can penetrate through thinner layers, offering glimpses of the atmosphere and surface below. By mapping Venus in 3D, Venus Express provided scientists with detailed insights into the planet's topography and geological activity. The spacecraft's data revealed a world shaped by ancient volcanic activity. Approximately 85% of Venus's surface is covered in solidified lava flows and extinct volcanoes. This volcanic history suggests that the planet was once geologically active, but it remains unclear whether any of these volcanoes are still erupting today. Additionally, the mission uncovered evidence of tectonic-like movements, further hinting at a dynamic past. Another remarkable discovery was the interaction between Venus's atmosphere and solar winds. With no magnetic field to protect it, Venus's upper atmosphere is constantly bombarded by solar particles, which strip away lighter molecules like hydrogen. This process likely contributed to the planet's loss of water, leaving it dry and inhospitable. As Venus Express continued its mission, it painted a sobering picture of what could happen if Earth's climate were to spiral out of control. Venus serves as a stark reminder of the power of greenhouse gases and the fragility of planetary ecosystems. While Earth is far from Venus's extreme conditions, rising carbon dioxide levels and global warming are pressing concerns for our planet's future. Venus's story is not just a tale of loss, but also one of resilience. Despite its hostile conditions, the planet remains a focus of scientific curiosity. Each discovery brings us closer to understanding not only Venus, but also our own planet's history and fate. Though Venus Express completed its mission in 2014, its legacy endures. The data it collected continues to shape our understanding of Venus and inspire new missions. Future spacecraft, such as NASA's Veritas and ESA's Envision, aim to build on Venus Express's findings, probing deeper into the mysteries of Earth's enigmatic twin. Venus may be inhospitable today, but its story reminds us of the delicate balance that makes Earth a haven for life. As we explore the solar system, Venus stands as a symbol of the complexities of planetary evolution and the urgent need to protect our fragile home. Venus, Earth's enigmatic twin, holds within its clouds the story of a transformation so profound that it turned a once watery, temperate planet into a blazing inferno. The Venus Express spacecraft, launched to uncover this mystery, made a groundbreaking discovery early in its mission. While studying the outer reaches of the atmosphere, it detected particles escaping into space, primarily helium, hydrogen, and oxygen. Among these, hydrogen and oxygen stand out as the fundamental components of water, the molecule that once defined Earth-like conditions on Venus. Yet today, only a faint trace of water vapor remains in Venus's thick, carbon dioxide-dominated atmosphere. If all this vapor were condensed, it would form a layer of water barely an inch deep across the planet's surface. For centuries, scientists speculated whether Venus ever had significant water. Some imagined vast oceans, perhaps covering 90% of the planet, similar to early Earth. However, the Venus Express findings shattered this hopeful vision. If Venus did possess oceans billions of years ago, their fate was as catastrophic as the planet's current state suggests. For years, the dominant theory was that these oceans simply boiled away due to Venus's proximity to the Sun. But as Venus Express continued its orbit, a more nuanced and unsettling explanation emerged. The Sun, the source of life on Earth, plays a dual role in shaping planetary fates. It provides light and warmth, but it also emits a relentless stream of charged particles known as the solar wind. These particles travel at speeds of up to 1.8 million miles per hour, carrying enough energy to strip away a planet's atmosphere if it lacks adequate protection. Earth is shielded by its magnetic field, a product of its fast rotation and molten iron core. This field acts as a protective bubble, deflecting the solar wind and preserving our atmosphere. Venus, however, rotates too slowly. One day on Venus lasts 243 Earth days and lacks the magnetic shield necessary to defend itself. Without this protection, the solar wind bombards Venus's upper atmosphere, stripping away molecules over time. Water, once a dominant feature of Venus's early environment, was not spared. Scientists now believe the planet's oceans evaporated into the atmosphere due to the intense heat from the Sun. There, ultraviolet radiation from sunlight broke apart the water molecules into hydrogen and oxygen. The lightweight hydrogen escaped into space, while the heavier oxygen remained for a time before being lost as well. Over billions of years, this relentless process drained Venus of its water, leaving behind a desolate, arid landscape. The loss of water marked the beginning of Venus's descent into hellish conditions, but it was the planet's greenhouse effect that sealed its fate. With no water to moderate the climate or sequester carbon dioxide, volcanic eruptions released trillions of tons of CO2 into the atmosphere. This set off a chain reaction. The thickening atmosphere trapped more heat, raising surface temperatures further. Unlike Earth, where the greenhouse effect remains in balance, Venus spiraled into a runaway greenhouse scenario. The result is a planet where temperatures soar higher than on Mercury, despite being farther from the Sun. On Earth, sunlight reaches the surface relatively unimpeded, warming the ground and creating a balanced climate system. Venus's dense atmosphere, however, absorbs most sunlight before it reaches the surface. The surface radiates heat in the form of infrared energy, but the thick atmosphere prevents this heat from escaping into space. Trapped in this cycle, Venus's surface and atmosphere grow ever hotter. A fiery example of what happens when climate regulation breaks down. The extreme conditions on Venus extend beyond its crushing heat and dense atmosphere. The planet's winds reveal another layer of its volatile nature. Despite Venus's slow rotation, its atmospheric winds are astonishingly fast, completing a full circuit around the planet in just 4 Earth days. This phenomenon, known as superrotation, is still not fully understood. The winds reach speeds of over 220 miles per hour, far surpassing the rotational velocity of the planet itself. These high-speed winds create a dynamic and chaotic atmosphere marked by massive cyclones at the poles and ferocious storms that dwarf even Earth's most violent hurricanes. Infrared imaging from Venus Express allowed scientists to peer through the dense clouds and observe these storms in action. The poles are particularly dramatic, with enormous vortexes churning the atmosphere in patterns that seem otherworldly. These cyclones, which are stable and long-lasting, hint at the complex interplay of heat, pressure, and wind within Venus's atmosphere. Venus is more than a scientific curiosity. It serves as a cautionary tale for Earth. Its transformation from a potentially habitable world to a scorching wasteland underscores the fragility of planetary ecosystems. The runaway greenhouse effect on Venus is an extreme version of what could happen on Earth if climate regulation fails. While Earth is shielded by its magnetic field and moderated by its oceans, rising carbon dioxide levels and global warming remind us of the delicate balance that sustains life here. Venus's story also raises questions about the future. Over cosmic timescales, even Earth's protective mechanisms may not be enough to prevent it from following Venus's path. As the sun ages and grows hotter, Earth may one day lose its oceans and atmosphere. Despite its hostile environment, Venus remains a focus of scientific exploration. Venus Express revolutionized our understanding of the planet, but many questions remain unanswered. How did Venus's volcanic activity shape its climate? Are any of its volcanoes still active today? What drives its super-rotating winds? Future missions, like NASA's Veritas and ESA's Envision, aim to delve deeper into these mysteries, building on the legacy of Venus Express. As we study Venus, we gain not only insights into its past, but also a deeper understanding of the forces that shape planets. Venus, once so similar to Earth, took a vastly different path. By unraveling its story, we might better understand our own planet's future and the fine line that separates a thriving world from a lifeless one. The atmosphere of Venus is a swirling enigma, moving at speeds that defy the slow rotation of the planet itself. Scientists call this phenomenon superrotation, where the planet's thick clouds race around the globe at speeds far exceeding its solid surface. On Venus, atmospheric winds complete a full circuit in just 4 Earth days, 60 times faster than the planet's rotation. To put this in perspective, if Earth's atmosphere behaved like Venus's, winds would whip around the planet at an unimaginable 50,000 miles per hour, completing a full rotation in just 30 minutes. On Earth, the atmosphere and surface move together in relative harmony. But Venus's atmosphere seems to operate independently, almost as if it has a mind of its own. What powers these extraordinary winds? The answer lies within Venus's thick cloud layer, which extends up to 12 miles and traps immense amounts of solar energy. Because Venus is closer to the Sun, its clouds absorb more energy, fueling wind speeds of over 200 miles per hour. Normal by Venusian standards, but extraordinary compared to Earth. This energy retention in the upper clouds, combined with the absence of surface-level moderation due to a lack of oceans, drives the breakneck speeds that define Venus's superrotation. Venus Express added another layer of intrigue to the planet's atmospheric study when it investigated a massive vortex at Venus's North Pole. This vortex resembled hurricanes on Earth, but with key differences. Hurricanes on our planet are fueled by warm, moist air rising from the ocean, creating a self-sustaining system as the sun's energy powers cloud formation and spinning winds. But Venus lacks oceans, so what fuels its hurricanes? As Venus Express swung into the southern hemisphere, it discovered a gargantuan vortex over the South Pole, 1,200 miles wide and 13 miles deep. This swirling storm was 4 times the size of Earth's largest hurricanes, with not one, but 2 rotating eyes. Scientists were astonished. What could sustain such a chaotic system? The answer lies in a combination of Venus's superfast winds and the planet's slow rotation. A process called the Coriolis effect plays a critical role. On a rotating planet like Venus, air heated at the equator moves toward the poles, but the planet's rotation deflects this movement. Instead of traveling in a straight line, the winds curve, creating spinning vortexes at the poles. On Earth, the Coriolis effect creates stable polar vortexes, but Venus's vortexes are anything but steady. The southern vortex observed by Venus Express constantly shifts, oscillating between different shapes and intensities. To understand this instability, scientists recreated the vortex in laboratory conditions. Using water to simulate Venus's atmosphere, they demonstrated that a thin spinning ring within the vortex caused oscillations, similar to the chaotic nature of Venus's polar storms. Adding dye to the simulation revealed the dramatic shifts occurring at the vortex's edges, mimicking the ever-changing dynamics of Venus's atmosphere. As Venus Express continued its observations, it detected a phenomenon that baffled and thrilled scientists in equal measure. On June 9, 2006, the spacecraft recorded an intermittent electromagnetic disturbance, a brief, low-frequency burst that resembled a whistle. This whistle was the signature of lightning. The discovery was groundbreaking, as lightning on Earth is closely tied to water, a resource Venus lost long ago. What then could generate lightning in Venus's dry and hostile atmosphere? Decades earlier, the Magellan mission uncovered evidence of widespread volcanic activity on Venus. These volcanoes released massive amounts of sulfur dioxide into the atmosphere. Over time, this gas mixed with residual water vapor to form clouds of sulfuric acid, the dominant component of Venus's clouds. Sulfuric acid, scientists theorized, plays the same role on Venus that water does on Earth, driving lightning by enabling electrical charge buildup. On Earth, thunderstorms occur when warm, moist air rises and cools, causing water droplets and ice crystals to collide and create electrical charges. Similarly, on Venus, the fast-moving sulfuric acid clouds rub together, building up positive and negative charges. When this electrical energy reaches a critical point, it discharges as lightning. The discovery of lightning in Venus's atmosphere provided compelling evidence of the dynamic and violent processes hidden beneath its dense clouds. Dr. Christopher Russell, a scientist on the Venus Express mission, had long suspected the existence of lightning on Venus. The data from the spacecraft confirmed his hypothesis and represented a personal triumph. The presence of lightning on Venus underscores the planet's raw, untamed power and hints at the dynamic forces that continue to shape its atmosphere. The implications of these findings reach beyond Venus. The study of its superrotation, polar vortexes, and lightning provides valuable insights into atmospheric dynamics that could apply to other planets, including Earth. Venus serves as a natural laboratory for understanding the extremes of weather and climate, offering clues about the conditions that might exist on exoplanets orbiting distant stars. Venus, with its searing heat, crushing pressure, and turbulent atmosphere, stands as one of the solar system's most hostile environments. Yet, it continues to captivate scientists with its mysteries. The discoveries made by Venus Express not only shed light on Venus's violent weather systems, but also highlighted the stark contrasts between Earth and its twin. Venus's superrotation, massive polar vortexes, and sulfuric acid-driven lightning paint a picture of a world shaped by forces both familiar and alien. These revelations deepen our understanding of planetary science and remind us of the delicate balance that sustains life on Earth. As future missions prepare to explore Venus further, we are left with the realization that the mysteries of our solar system's fiery twin are far from solved. Each new discovery brings us closer to answering the ultimate question: what does Venus's past reveal about the future of Earth? To explore the possibility of life on Venus, scientists study extremophiles, microorganisms that thrive in the harshest environments on Earth. Biologist Lynn Rothschild has identified microbes living in acidic hot springs in Yellowstone National Park. an environment that closely mimics Venus's atmospheric conditions. These organisms, such as red algae thriving in acidic streams with pH levels as low as 3 and temperatures of 40 degrees Celsius, offer a glimpse into how life might adapt to Venus's extreme environment. The geysers in Yellowstone, powered by volcanic activity, resemble the sulfuric conditions found on Venus. The discovery that life can flourish in these seemingly inhospitable conditions strengthens the argument that Venus's clouds, despite their sulfuric acid content, could harbor similar life forms. The acidic droplets in Venus's clouds could act as habitats for microorganisms, much like the hot, acidic waters of Yellowstone. The idea that Venus might still be geologically and biologically active is reshaping our understanding of the planet. Active volcanoes, evidence of ancient oceans, and the possibility of microbial life challenge the notion of Venus as a dead world. Instead, Venus may be a dynamic and evolving planet with much more to reveal. As future missions prepare to explore Venus in greater detail, scientists hope to answer the questions raised by Venus Express. Could there be life hiding in the clouds of this infernal world? What drives its volcanic activity, and what does it tell us about planetary evolution? Venus, once considered Earth's twin, may hold secrets that shed light on our own planet's past and its potential future. Despite its hellish reputation, Venus continues to challenge our understanding of what it means to sustain life. Extremophiles on Earth, such as cyanidium algae, thrive in conditions that mimic those on Venus. These remarkable organisms endure extreme heat, acidity, and even environments dominated by carbon dioxide, conditions that would be fatal to most forms of life. What makes cyanidium especially intriguing is its ability to survive and photosynthesize in pure CO2, levels even higher than those found in Venus's dense atmosphere. The possibility that life might exist on Venus centers not on its brutal surface, where temperatures reach 900 degrees Fahrenheit and pressures are 90 times that of Earth, but in its clouds. 30 miles above the surface, the conditions are less extreme, with temperatures around 176 degrees Fahrenheit, well within the range some microbes on Earth can tolerate. Scientists speculate that if life once began in Venus's ancient oceans, it may have migrated to the cooler cloud layers as the water evaporated, finding refuge in the acidic environment. One major question remains: how could life survive without liquid water? Venus's clouds contain water vapor, and some terrestrial organisms, such as lichens, have evolved to extract water directly from vapor. This discovery gives hope that Venus's cloud-dwelling microbes could sustain themselves similarly. To test this idea, biologist Lynn Rothschild and her team have simulated Venus-like conditions on Earth. By collecting air samples above acidic hot springs that resemble Venus's clouds, they've demonstrated that microbes can indeed survive in such environments. Rothschild's experiments have gone even further. She launched microorganisms into Earth's upper atmosphere, an environment with extreme cold, low pressure, and intense radiation, to see how they would fare. Many of the microbes survived, and some even showed signs of being able to reproduce. This resilience supports the idea that life could persist in Venus's long-lived clouds, reproducing and forming self-sustaining colonies within the swirling acidic haze. On Venus, the continuous cloud layers provide a potential habitat for life. Though particles in the clouds eventually fall out, any microbial life could potentially reproduce fast enough to maintain a self-sustaining population. The dark patches in Venus's clouds, first observed by Venus Express, absorb ultraviolet light in patterns that suggest something unusual is occurring. Could these patches be home to microorganisms? While definitive proof remains elusive, The idea is no longer science fiction. After 100 weeks and 87 million miles of data collection, Venus Express painted a compelling picture of Venus's past, a planet with Earth-like conditions, vast oceans, and perhaps even the building blocks of life. While Venus succumbed to its proximity to the Sun, its sister Earth flourished. Yet, even in Venus's hostile environment, life may persist, hidden in its clouds. Future missions may one day unlock this mystery, potentially discovering the holy grail of space exploration, life beyond our world. Until then, Venus continues to inspire and intrigue, a testament to the resilience of life in the most unexpected places. Venus, often called Earth's twin, presents one of the greatest mysteries of the solar system. Once thought to be similar to Earth in size, composition, and potentially environment, Venus is now a harsh, unforgiving world. Its clouds are made of corrosive sulfuric acid, and its surface temperature of 900 degrees Fahrenheit is hot enough to melt lead. What turned this planet, once likely similar to Earth, into a searing wasteland? Scientists are on a mission to uncover the answer, as understanding Venus may hold vital lessons about Earth's future. In 2005, the European Space Agency launched Venus Express, a probe tasked with unraveling the planet's secrets. This mission marked a pivotal moment in the study of Venus, aiming to uncover why it evolved so differently from Earth, despite starting with similar conditions. The craft traveled 250 million miles to reach its destination, equipped with state-of-the-art instruments designed to peer through Venus's thick atmosphere and study its surface without landing. For centuries, Venus was an enigma. Shrouded in dense clouds, its surface remained hidden from view. Early scientific assumptions portrayed Venus as a tropical paradise, with temperatures akin to Earth's. Some even imagined lush jungles thriving in a warm, humid atmosphere. By the mid-20th century, however, data revealed a far bleaker reality. Soviet missions in the 1960s and 70s, such as the Venera program, painted a picture of an alien world, a desolate, dusty desert with no water, and an atmosphere composed almost entirely of carbon dioxide. Venus and Earth were likely formed from the same cloud of gas and dust over 4 billion years ago, and they share similar size and density. However, while Earth developed oceans, life, and a habitable climate, Venus became a vision of hell. Its surface is 85% extinct volcanoes and solidified lava flows. Its crushing atmospheric pressure is 90 times that of Earth, enough to flatten a car. Most alarmingly, Venus's runaway greenhouse effect caused temperatures to soar to extraordinary levels, with rocks glowing in the dark due to the intense heat. The key to Venus's transformation lies in its thick atmosphere of carbon dioxide. On Earth, this gas is a natural part of the greenhouse effect, trapping heat and maintaining a climate suitable for life. However, Venus's atmosphere traps heat so effectively that it turned the planet into an inferno. While Earth's carbon dioxide levels are causing slight warming, Venus serves as a cautionary tale of what happens when the greenhouse effect spirals out of control. When Venus Express approached the planet, the mission faced its first major challenge: achieving orbit. The craft had to reduce its speed by 3,000 miles per hour to be captured by Venus's gravity. Too fast, and it would fly past into deep space. Too slow, and it would crash into the planet's surface. The team on Earth anxiously waited as the spacecraft disappeared behind Venus for 10 minutes during the braking maneuver. Finally, Venus Express re-established communication, signaling that it had successfully entered orbit. The spacecraft's elliptical path brought it as close as 155 miles above the planet's surface, allowing its instruments to study Venus in unprecedented detail. This mission was a technological leap forward from earlier efforts. Unlike past probes that had short lifespans due to Venus's extreme conditions, Venus Express was designed to observe the planet from orbit, safe from the crushing pressure and intense heat. One of its groundbreaking tools was an infrared imaging system, which allowed scientists to see through the dense clouds obscuring Venus's surface. Infrared light can penetrate the thinner areas of the cloud cover, revealing the planet's lower atmosphere and surface features in 3D for the first time. These observations shed light on Venus's geological history, including its volcanic activity and how its atmosphere interacts with the surface. The mission's findings were startling. Venus's surface is not only scorched, but appears dynamic in ways scientists are still trying to understand. Volcanoes, though extinct, may still influence the atmosphere, while the thick clouds of sulfuric acid create an otherworldly environment where sunlight struggles to penetrate. Understanding how Venus evolved from a potentially Earth-like world into a hellish wasteland is crucial for understanding Earth's future. Could the two planets' fates be linked? Venus Express provided data suggesting that the runaway greenhouse effect played a central role in Venus's transformation. If similar processes were to take hold on Earth due to unchecked carbon emissions, our planet could follow a similar trajectory. The mission also raised profound questions about habitability and life elsewhere in the solar system. Could Venus have once harbored oceans or microbial life before its climate catastrophically changed? If so, studying Venus could help scientists identify similar processes on exoplanets in distant star systems. Venus Express was not just a scientific triumph, but a warning. It demonstrated the fragility of planetary systems and how small changes in atmospheric composition can lead to dramatic, irreversible consequences. The data it gathered has deepened our understanding of Venus, while providing invaluable insights into Earth's climate challenges. The lessons from Venus are clear. While our planet remains habitable, the balance is delicate. Venus stands as a stark reminder of what can happen when a planet's atmosphere spins out of control. As scientists continue to analyze the findings from Venus Express, they hope to uncover not just the mysteries of our closest planetary neighbor, but also the keys to preserving our own world. This new understanding of Venus is both inspiring and sobering. By studying its transformation, we gain a deeper appreciation for the conditions that sustain life on Earth and the urgent need to protect them. The story of Venus is not just about the past of another planet. It may also be a glimpse into what could lie ahead for our own. Venus, often called Earth's twin, hides beneath its dense clouds a tale of transformation that serves as both a scientific mystery and a warning. While the planet shares many similarities with Earth in size and composition, its evolution took a drastically different path. Today, Venus is a searing wasteland with clouds of sulfuric acid and surface temperatures reaching 900 degrees Fahrenheit, hot enough to melt lead. Understanding how Venus turned from a potentially habitable world into the hottest planet in the solar system could provide critical insights into Earth's future. The European Space Agency's Venus Express mission, launched to uncover the secrets of Venus, utilized advanced infrared imaging technology to look beyond the planet's thick cloud cover. Unlike visible light, which reflects off the uppermost layers of Venus's atmosphere, infrared light penetrates these dense hazes, revealing the lower atmosphere and surface features. From its vantage point 155 miles above the surface, Venus Express mapped the planet with unprecedented detail, offering scientists their best look yet at Venus's geology and atmosphere. Infrared imaging showed striking differences between Venus and Earth. Once considered potential twins, the two planets have diverged dramatically over billions of years. The mission set out to answer why. Despite decades of exploration, Venus continues to surprise scientists, and Venus Express soon made a groundbreaking discovery. While observing the outer atmosphere, Venus Express detected particles escaping into space, mainly hydrogen, helium, and oxygen. These elements are essential components of water, raising questions about Venus's past. Scientists have long debated whether Venus once had oceans. Some theorize that early Venus, like Earth, could have been covered by water, with oceans spanning 90% of the planet's surface. Yet Venus Express revealed that only trace amounts of water vapor remain in the atmosphere. If condensed, this vapor would form a layer of water barely an inch deep. If Venus once had vast oceans, what happened to them? For years, the prevailing theory was that the oceans simply boiled away due to Venus's proximity to the Sun. However, data from Venus Express suggested a more complex explanation. The Sun, while essential for life on Earth, also emits a relentless stream of charged particles known as the solar wind. Traveling at speeds of up to 1.8 million miles per hour, the solar wind can strip away unprotected planetary atmospheres. On Earth, our magnetic field, generated by the movement of molten iron in the planet's core, acts as a protective shield, deflecting the solar wind and safeguarding our atmosphere. Venus, however, lacks such a magnetic field. Its extremely slow rotation, 1 Venusian day equals 243 Earth days, may prevent the generation of this crucial defense. Without a magnetic shield, Venus's atmosphere is fully exposed to the solar wind, allowing particles to escape into space. Scientists now believe that Venus's proximity to the Sun initiated the loss of its water. The planet's intense heat caused its oceans to evaporate, filling the atmosphere with water vapor. Ultraviolet radiation from the Sun then broke the water molecules into hydrogen and oxygen. The lightweight hydrogen escaped into space, while the oxygen likely reacted with surface minerals or was also stripped away by the solar wind. Over billions of years, Venus's oceans vanished entirely. As water disappeared, Venus's atmosphere transformed from one dominated by water vapor to one saturated with carbon dioxide. Ancient volcanoes released massive amounts of CO2, further intensifying the greenhouse effect. On Earth, the greenhouse effect keeps our planet warm and habitable. But on Venus, this process spiraled out of control. In Venus's thick atmosphere, 100 times denser than Earth's, sunlight is trapped before it can reach the surface. Any infrared radiation emitted from the planet's surface is absorbed by the CO2-rich atmosphere and reflected back, creating a feedback loop that traps heat. Over time, this runaway greenhouse effect drove surface temperatures to catastrophic levels, turning Venus into a burning inferno. If you find this video helpful, please give us a subscribe. A small compliment from you is a huge motivation for us. Mars. From the fiery inferno of Venus, we now journey to the cold, dusty plains of Mars. Once thought to be Earth's twin in its own way, the red planet holds tantalizing clues to ancient rivers, lakes, and perhaps even life. Let's uncover the secrets of this mysterious neighbor. Life as we know it thrives on Earth, where water is the lifeblood of ecosystems and the essential ingredient for existence. Scientists searching for life beyond our planet always start by looking for liquid water, the critical environmental requirement for all known organisms. This quest has taken us to an alien world that seems to defy the laws of physics. a place where water should not exist, but where compelling evidence suggests it once flowed abundantly. Welcome to Mars, the red planet, where a hidden history of water might hold the key to finding extraterrestrial life. On August 4, 2007, a Delta II rocket carrying NASA's Phoenix lander blasted off from Cape Canaveral, embarking on a 400 million-mile journey to Mars. As the first robotic scout mission under NASA's Mars exploration program, Phoenix was designed to explore the planet's Arctic plains and search for the building blocks of life: carbon, nitrogen, and, most crucially, water. By following these clues, Phoenix aimed to answer one of humanity's most profound questions: whether life is unique to Earth or if the universe is teeming with it. After months of travel through the void of space, Phoenix entered the Martian atmosphere on May 25, 2008. As the lander approached the surface, engineers at NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California, held their breath. Successfully landing on Mars is a monumental challenge. Only a fraction of missions to the Red Planet have survived the perilous descent. But Phoenix prevailed, touching down in the Martian Arctic to begin its groundbreaking exploration. The primary goal of the Phoenix mission was to determine whether Mars's Arctic plains could support life, either now or in the past. While Phoenix was not equipped to detect life directly, it sought evidence of water, the single unifying factor for all life on Earth. Planetary scientist Chris McKay explained the rationale. When we look at life on Earth, we see incredible diversity. But the one thing all organisms share is the need for liquid water. It's the foundation for everything. That's why our search for life always begins by searching for water. Mars's surface today appears dry, barren, and inhospitable. But the red planet wasn't always this way. Decades of observations, starting with NASA's Mariner 9 spacecraft in 1971, revealed tantalizing clues of a wetter past. Images from Mariner 9 showed vast channels and valleys that appeared eerily similar to water-carved features on Earth. These discoveries sparked decades of debate. How could a planet with a thin, freezing atmosphere have sustained flowing water? Mars's current atmosphere presents two major challenges for water. First, the air pressure is less than 1/100th of Earth's, equivalent to being 20 miles above sea level here. A height nearly 4 times the altitude of Mount Everest. At this low pressure, water cannot remain stable as a liquid. Instead, it would boil away at temperatures as low as 50 degrees Fahrenheit, 10 degrees Celsius. Second, Mars is incredibly cold, with average temperatures ranging from minus 225 degrees Fahrenheit to minus 143 degrees Celsius at its poles, to a maximum of 70 degrees Fahrenheit to 20 degrees Celsius during the warmest days at the equator. Even if liquid water could exist briefly on the surface, it would quickly freeze solid. These conditions create a paradox. Mars's surface is both too cold and too low pressure for liquid water to exist. Yet the features observed, vast networks of valleys, channels, and gullies, strongly resemble those created by water erosion on Earth. Scientists considered alternative explanations, such as carbon dioxide, lava flows, or wind erosion. But none could account for all the observed features. The evidence suggested that water had flowed across Mars in the past. But when and under what conditions? In June 2000, images from the Mars Orbiter camera aboard the Mars Global Surveyor revealed astonishing evidence of recent water activity. These images showed gullies and alcoves on slopes in Mars's southern hemisphere, features that closely resemble those created by flowing water on Earth. The patterns, reminiscent of veins in a leaf or branching tree roots, appeared on slopes that received minimal sunlight, some of the coldest parts of the planet. Could liquid water still exist on Mars? NASA's Phoenix lander was sent to investigate this question directly. Using advanced instruments, it analyzed the Martian soil and atmosphere, searching for water and the conditions necessary for life. Early in its mission, Phoenix discovered water ice just below the surface, a major breakthrough. By scraping away the topsoil, the lander exposed bright, icy material that sublimated into vapor when exposed to the thin Martian atmosphere. This confirmed the presence of water ice and provided further evidence that Mars might once have had liquid water. Another key piece of evidence comes from a meteorite known as Allen Hills 84001, discovered in Antarctica in 1984. This 6-inch rock, weighing over 4 pounds, is one of only 34 known Martian meteorites on Earth. Dating back 4.5 billion years, it is older than any rock found on our planet. Astrobiologist Dr. David McKay of NASA's Johnson Space Center analyzed this meteorite and found microscopic globules of iron and magnesium carbonates, minerals that form in the presence of liquid water. These findings suggest that water once flowed on Mars 3.9 billion years ago, under conditions that might have supported life. Mars rovers like Spirit, Opportunity, and Curiosity have continued the search for water, sending back compelling evidence of Mars's wetter past. At Meridiani Planum, the landing site of Opportunity, the rover discovered spherical rocks nicknamed blueberries scattered across the landscape. These formations, composed of hematite, are typically formed in the presence of water, further confirming Mars's aqueous history. If water once flowed freely on Mars, could the planet have supported life? On Earth, life persists in the harshest environments. Organisms thrive in deep-sea hydrothermal vents, acidic hot springs, and even beneath Antarctic ice. The discovery of water ice and hydrated minerals on Mars raises the possibility that microbial life could exist, either as remnants of a distant past or in isolated subsurface reservoirs today. Scientists have proposed that liquid water might exist transiently on Mars's surface, perhaps during brief warming periods caused by volcanic or meteorological events. The discovery of recurring slope lineae, RSL, dark streaks that appear seasonally on Martian slopes, suggests that briny water might occasionally flow, albeit in minute quantities. Mars's watery past not only informs us about the planet's potential for life, but also provides insight into the early solar system. Understanding how Mars lost its water and transitioned to its current state could help scientists predict Earth's long-term future and guide the search for habitable planets around other stars. The possibility of water on Mars and the life it might have sustained remains one of the most exciting questions in planetary science. As missions like Mars Sample Return and the ESA's ExoMars rover prepare to delve deeper into the planet's mysteries, humanity edges closer to uncovering the truth about our enigmatic neighbor. For now, Mars continues to captivate scientists and dreamers alike. With its icy poles, ancient riverbeds, and mysterious gullies, the red planet remains a tantalizing puzzle, hinting at a time when it may have been more like Earth. Whether life ever took hold on Mars or still clings to existence in its subsurface or clouds, remains an open question. But one thing is certain: Mars's story is far from over. As new missions set their sights on its rusty terrain, the quest to follow the water continues, offering the hope that one day we might find the answer to one of humanity's greatest mysteries. The story of Mars is one of transformation, marked by its transition from a warm, wet world to the frozen desert we see today. Central to this narrative is water, once abundant, now elusive. Evidence of Mars's watery past continues to captivate scientists, offering tantalizing clues about the planet's history and its potential to support life. At the heart of this exploration is NASA's Phoenix lander, a mission designed to dig beneath the Martian surface and uncover the secrets of water on the red planet. One of the most compelling pieces of evidence for Mars's aquatic history comes in the form of small spherical rocks scattered across its surface, nicknamed blueberries by NASA scientists. These peculiar formations, made of hematite, closely resemble deposits found near Earth's hot springs and ancient lake beds, such as those near Yellowstone National Park and Lake Superior. Their presence on Mars's Meridiani Planum suggests that this vast plain was once saturated with water, or possibly even the site of an ancient lake. Further exploration of Mars's surface reveals even more evidence of a water-rich past. High-resolution images from the Mars Express spacecraft show geological features like Ionic Chaos, a large depression, and Ares Vallis, an outflow channel. These formations resemble ancient river systems carved by catastrophic floods. According to planetary geologist Jim Rice, these floods were on a scale unlike anything on Earth. If you took every river on Earth and put them in one spot, flowing at the same time, some of these flood channels on Mars would still be 20 to 30 times bigger. The evidence of ancient rivers, valleys, and catastrophic floods raises a fundamental question. How did Mars transition from a warm, wet planet to the cold, dry world we see today? Understanding this transformation is one of the key goals of the Phoenix mission. Scientists believe that for water to have existed on the Martian surface, the planet must have had a thicker atmosphere and higher temperatures in its past. Mars's early history suggests that these conditions did exist, but they were short-lived. Mars's smaller size played a critical role in its cooling and atmospheric loss. When the solar system formed 4.6 billion years ago, both Earth and Mars were molten balls of lava. Over time, as they cooled, Mars's smaller diameter allowed it to shed heat more rapidly than Earth. This rapid cooling stabilized liquid water on Mars's surface far earlier than on Earth, creating conditions that might have supported lakes, rivers, and even rain. The source of Mars's water likely came from comets and asteroids, which bombarded the planet in its early history. Unlike Earth, where intense heat caused water to boil away, Mars was cool enough to retain much of the water delivered by these icy bodies. By 3.9 billion years ago, Mars had a temperate climate, a thick atmosphere, and liquid water, ideal conditions for life to potentially emerge. While Mars was once warm and wet, it could not hold on to these conditions indefinitely. Scientists theorize that a combination of factors led to the loss of its water. Unlike Earth, Mars lacked a strong magnetic field to shield its atmosphere from the sun's solar wind. As Mars's core cooled and its magnetic field weakened, the solar wind stripped away much of the atmosphere. Without sufficient atmospheric pressure, water on the surface boiled away or froze, leaving behind the desolate landscape we see today. In 2003, NASA's Odyssey orbiter provided key insights into Mars's remaining water. Using a gamma-ray spectrometer, it mapped hydrogen levels in the top 3 feet of the Martian surface, revealing frozen water reservoirs near the planet's poles. These reservoirs contain enough water to cover Mars's surface with a layer 6 to 10 meters deep, if melted. Phoenix's mission was to confirm the presence of this ice and unravel the story of its formation and fate. Phoenix represented a significant leap in Martian exploration. Unlike previous missions that focused on the surface, Phoenix was equipped to dig beneath the ground and analyze subsurface ice. Its robotic arm, capable of scraping soil and delivering samples to its onboard laboratory, allowed scientists to study the composition of Martian ice and soil at unprecedented depths. The lander's thermal and evolved gas analyzer, TEGA, was a key instrument in this endeavor. TEGA's 8 tiny ovens, each the size of a pen cartridge, were designed to vaporize ice and soil samples at temperatures up to 1,800 degrees Fahrenheit. As the samples vaporized, they released gases that TEGA analyzed for traces of hydrogen, oxygen, carbon, and nitrogen, the building blocks of life. By sampling at different depths, Phoenix aimed to map the history of water on Mars and uncover clues about the planet's potential to harbor life. The evidence uncovered by Phoenix and other missions continues to deepen the mystery of Mars's water. Images from the Mars Global Surveyor showed modern-looking gullies and alcoves on slopes in the planet's southern hemisphere. These features, resembling Earth's water-carved gullies, suggest that liquid water might still occasionally flow on Mars. Some scientists hypothesize that geothermal activity beneath the surface periodically melts subsurface ice, causing brief episodes of liquid water flow. This process could also release greenhouse gases, temporarily warming the planet and creating unstable conditions conducive to water. The discovery of these gullies adds weight to the idea that Mars's core remains geologically active. Although Mars lacks plate tectonics, its residual heat might periodically cause bursts of volcanic or geothermal activity, melting ice and creating the fleeting wet spots observed on its surface. One of the most intriguing pieces of evidence for Mars's watery past comes from the Allen Hills 84001 meteorite. Discovered in Antarctica in 1984, this ancient rock dates back 4.5 billion years and contains microscopic globules of carbonate minerals. These minerals, formed in the presence of liquid water, provide direct evidence that Mars once had a wetter climate capable of supporting flowing water. Radiometric dating of the carbonate globules suggests that liquid water was present on Mars as recently as 3.9 billion years ago. If Mars once had water, could it also have supported life? On Earth, water is synonymous with life. Even in the harshest environments, acidic hot springs, deep-sea hydrothermal vents, and polar ice caps, microbial life thrives. Mars's ancient lakes and rivers might have provided a similar environment for life to emerge. The discovery of water ice and hydrated minerals on Mars raises the possibility that microbial life might still exist, hidden beneath the surface or clinging to transient reservoirs of liquid water. The Phoenix mission marked a significant step forward in our understanding of Mars, but the Red Planet's story is far from complete. Future missions, such as NASA's Perseverance rover and the ESA's ExoMars rover, aim to build on Phoenix's findings, searching for direct evidence of life and studying the planet's geological history in greater detail. Mars, once a warm, wet world, now stands as a frozen testament to the fragility of planetary ecosystems. By studying its past, scientists hope to better understand the processes that shape planetary climates and determine the potential for life beyond Earth. The red planet continues to beckon, its ancient riverbeds and frozen plains whispering stories of a time when it might have been not so different from our own world. As humanity pushes further into the cosmos, Mars remains one of the most tantalizing destinations, a place where the mysteries of water, life, and planetary evolution converge. Mars's frozen desert landscape might seem inhospitable, but its geology holds uncanny similarities to Earth's. Both planets feature volcanoes, canyons, and valleys, but Mars's resemblance to Earth doesn't end there. For planetary scientists, regions on Earth such as Antarctica's dry valleys serve as analogues to the Martian environment, offering clues to the potential for life on the red planet. Mars, at its warmest and wettest, would have been like Earth at its coldest and driest, explains planetary scientist Chris McKay. These comparisons guide NASA's Phoenix mission as it hunts for the building blocks of life buried in the icy soils of Mars. On Earth, McKay and his colleague Peter Smith prepare for the Phoenix mission by digging into the ice-covered soils of Antarctica. This exercise mirrors what Phoenix will do on Mars, testing instruments and techniques designed to detect evidence of life. We're analyzing soil layer by layer down to the ice, says McKay. By examining these frozen soils, they hope to connect findings on Earth to potential discoveries on Mars. In the Antarctic's sub-zero temperatures, life takes the form of extremophiles, microorganisms adapted to thrive in conditions as harsh as those on Mars. Extremophiles were first discovered in the boiling hot springs of Yellowstone National Park, but their diversity stretches far beyond heat. They thrive in supersaline environments, deep ocean vents, and even uranium-laden waters near nuclear reactors. Yet it's the microbes living in Antarctica's frozen deserts that captivate researchers like Smith. If life can survive transient amounts of liquid water here, he muses, why not on Mars? Phoenix aims to answer this question by searching for ice, organics, and evidence of past habitable conditions. Mars's polar deserts preserve evidence of its past climate in much the same way Earth's permafrost preserves ancient life forms. In Siberia, frozen mammoths have been unearthed after tens of thousands of years, offering glimpses into the distant past. On Mars, the Phoenix team hopes for a similar effect. We're looking for micro-Martian mammoths, McKay jokes, referring to microbial evidence frozen in Martian ice for billions of years. Phoenix's instruments are uniquely equipped for this search, with the ability to detect organics, carbon-based compounds essential for life, and analyze the history and properties of Martian ice. Phoenix's robotic arm digs beneath the Martian surface to collect samples, which are then delivered to a suite of onboard instruments. Among these is the Thermal and Evolved Gas Analyzer, TIGA, which vaporizes samples at temperatures up to 1,800 degrees Fahrenheit, releasing gases for analysis. These gases are scanned for hydrogen, oxygen, carbon, and nitrogen, the elements of life. By studying soil and ice at different depths, Phoenix builds a map of Mars's water history, providing insights into how ice interacts with soil and atmosphere. While Phoenix was purpose-built to dig into Mars's icy soils, one of the most compelling discoveries of water on Mars came from an accidental breakdown. In 2007, NASA's Spirit rover uncovered evidence of past water when its malfunctioning wheel dragged through the soil, revealing an unexpected find: nearly pure silica. That was a serendipitous discovery, recalls one scientist. On Earth, high levels of silica are typically found in hot springs and fumaroles, environments teeming with microbial life. This find suggested that ancient Mars once had similar conditions, supporting the possibility of life. The discovery reignited debates about the red planet's habitability. Could Martian extremophiles have thrived in these silica-rich environments, much like their counterparts on Earth? Spirit's findings bolstered the argument that Mars had habitable zones in its past, and perhaps still does. The discovery of potential habitable zones on Mars brought renewed attention to the Allen Hills meteorite, a 4 billion-year-old rock found in Antarctica in 1984. Jupiter, the solar system's largest planet, is a world of extremes. With its massive size, swirling storms, and mysterious moons, this gas giant has captivated scientists and astronomers for centuries. Now, with missions like Galileo, Juno, and the upcoming Europa Explorer, humanity is unraveling the secrets of this enigmatic planet and its vast system of moons. From the Great Red Spot to the ice-covered mysteries of Europa, Jupiter's story is one of wonder, violence, and discovery. In 1989, NASA launched the Galileo spacecraft aboard the Space Shuttle Atlantis, setting it on a 6-year journey to Jupiter. Reaching a planet 500 million miles away posed immense challenges. Carrying enough fuel was impossible, so NASA engineers devised a brilliant workaround: a gravitational slingshot. By flying close to Venus and then Earth, Galileo used the planet's gravity to gain the momentum needed to reach Jupiter. This innovative approach wasn't the only stroke of luck for the mission. As Galileo approached its destination, a remarkable event unfolded. A comet, Shoemaker-Levy 9, SL9, was on a collision course with Jupiter. It was an unprecedented opportunity to observe a cosmic impact up close. David Levy, one of the comet's discoverers, described the anticipation. This was going to be the first time in recorded history that we would witness a comet colliding with a planet. We had no idea what we might learn. As the day of impact approached, the world watched. Telescopes on mountaintops and in space focused on Jupiter, capturing every detail. Scientists debated the outcome. Would Jupiter's dense atmosphere swallow the comet whole, leaving no trace? Or would the impact reveal the planet's inner secrets? What followed was beyond anyone's expectations. The fragments of SL9 slammed into Jupiter with unimaginable force, creating massive plumes of gas and debris that rose thousands of miles into the atmosphere. The explosions left dark scars on Jupiter's surface, visible even through small telescopes on Earth. For scientists, the impact was a treasure trove of data, providing insights into Jupiter's composition. As material from the planet's interior was stirred up and ejected, it became clear that Jupiter was not just a frozen relic of the solar system's formation. It was a dynamic, evolving world. Jupiter's immense size, 11 times larger than Earth and 318 times its mass, makes it a key piece in understanding the solar system's history. Scientists believe that Jupiter formed early in the Sun's life, capturing leftover gas and dust. This process, similar to how stars form, resulted in a planet composed mostly of hydrogen and helium, the same elements that dominate the Sun. By studying Jupiter, scientists hope to learn more about how planets emerge and evolve. The Great Red Spot, a colossal storm that has raged for at least 400 years, offers another glimpse into the planet's turbulent history. With winds exceeding 250 miles per hour and a size large enough to engulf 3 Earths, the storm exemplifies Jupiter's extreme weather. Galileo and later missions like Juno have studied this and other atmospheric phenomena, revealing a world of dynamic winds, lightning superbolts, and shifting weather patterns. Jupiter's 63 moons form a miniature solar system, each with unique characteristics. Galileo focused on the 4 largest, Io, Europa, Ganymede, and Callisto, known as the Galilean moons. Io, the most volcanically active body in the solar system, Io is a world of fiery eruptions and sulfurous plumes. Its intense geological activity is driven by tidal forces from Jupiter's immense gravity, which stretch and heat the moon's interior. Europa, perhaps the most intriguing of Jupiter's moons, Europa is covered in a thick shell of ice. Beneath this frozen crust lies a global ocean of liquid water, kept warm by the same tidal forces that power Io's volcanoes. Where there is water, there could be life, making Europa a prime target for future exploration. Ganymede, the largest moon in the solar system, Ganymede is bigger than the planet Mercury. Its surface is a mix of old, heavily cratered regions and younger, grooved terrain. Ganymede is also unique in having its own magnetic field, a feature rare among moons. Callisto, the most heavily cratered object in the solar system, Callisto's ancient surface is a relic of the early solar system. Its lack of geological activity contrasts sharply with Io and Europa, offering a stark reminder of the diversity among Jupiter's moons. The Galileo mission marked the beginning of a new era in the study of Jupiter, but it was just the start. The Juno spacecraft, currently orbiting Jupiter, is providing unprecedented data on the planet's gravity, magnetic field, and atmospheric dynamics. Meanwhile, the Europa Clipper mission, set to launch in the 2030s, will focus on Europa's subsurface ocean, searching for signs of habitability and potential life. Another ambitious project, the underwater probe Endurance, aims to one day penetrate Europa's icy crust and explore its hidden ocean. If successful, this mission could answer one of humanity's most profound questions. Are we alone in the universe? From its colossal storms to its dynamic moons, Jupiter stands as a testament to the diversity and complexity of the solar system. The Galileo mission's discoveries reshaped our understanding of this gas giant, revealing a world far more dynamic and mysterious than anyone had imagined. Jupiter's immense gravity and rich history continue to make it a focal point for planetary science. As new missions take up the torch, Jupiter and its moons will remain at the forefront of the search for life and the study of planetary formation. With each discovery, humanity moves closer to understanding not only the secrets of the Jovian system, but also our own origins and place in the cosmos. Jupiter's vast size and dynamic atmosphere have long intrigued scientists. With its swirling storms, powerful lightning, and ever-changing weather, this gas giant is a playground for planetary exploration. Missions like Galileo have brought humanity closer to understanding the secrets of Jupiter, revealing an alien world whose mysteries challenge our understanding of planetary formation and atmospheric physics. One of Galileo's most daring experiments involved releasing a small probe into Jupiter's clouds to analyze the planet's atmosphere. As the probe descended, it measured wind speeds and temperatures at various depths, offering scientists their first glimpse into the mechanics of Jupiter's violent weather systems. It was also tasked with answering a fundamental question. Is Jupiter a failed star, similar in composition to the Sun, or something entirely different? Scientists eagerly awaited data confirming the existence of a layer of water vapor, thought to have been revealed by the impact of comet Shoemaker-Levy 9. But as the probe descended, it encountered a surprising and puzzling phenomenon. Instead of water, the probe found itself drifting through dry, wispy gases in a downdraft, a dry gap in Jupiter's atmosphere. This unexpected discovery hinted at a complex system of long-term weather patterns, with alternating regions of dry and wet areas, challenging previous assumptions. Despite its limited time in Jupiter's atmosphere, the probe revolutionized our understanding of the planet. It detected an abundance of heavy elements, such as argon, krypton, carbon, and nitrogen, at levels 2 to 3 times higher than those found in the Sun. These elements could only condense at extremely low temperatures, far colder than Jupiter's current position. This discovery suggested that Jupiter did not form where it currently resides, but may have originated in the outer solar system, where temperatures are colder and later migrated inward. The implications were staggering. This little probe, in one fell swoop, showed us that all of our ideas about how planets formed were wrong, a scientist explained. The findings reshaped theories about planetary formation and the early solar system, but much remained unanswered. After just 58 minutes of groundbreaking data transmission, the probe succumbed to Jupiter's crushing atmospheric pressure, leaving behind tantalizing questions for future missions. In 2011, NASA launched the Juno spacecraft to build on Galileo's discoveries. Equipped with cutting-edge instruments, Juno aimed to map the water content across Jupiter's entire atmosphere using microwave radiometry. By analyzing the distribution of water, scientists hoped to unlock the recipe for Jupiter's formation, providing new insights into how planets, including Earth, came to be. Jupiter's atmosphere is a maelstrom of turbulence, featuring hurricane-like vortices, powerful lightning, and swirling clouds. Its most iconic feature, the Great Red Spot, has raged for over 300 years. With winds exceeding 250 miles per hour and a size large enough to engulf 3 Earths, this colossal storm is a centerpiece of Jupiter's dynamic weather system. Understanding how such storms form and persist for centuries remains one of the biggest challenges for scientists. Unlike Earth's weather, powered by the Sun's heat, Jupiter is too far from the Sun for solar energy to drive its storms. Instead, scientists suspect that internal heat from Jupiter's core powers its weather systems. Using Galileo, scientists analyzed smaller white ovals near the Great Red Spot. These spots, caused by convection and rapidly rising air, were thought to be thunderstorms. To confirm this, Galileo observed the night side of Jupiter, where it identified intense lightning strikes concentrated within the white ovals. These lightning bolts, 1,000 times more powerful than those on Earth, provided critical evidence of thunderstorms feeding energy into the planet's atmosphere. One of the most remarkable phenomena observed by Galileo was the merging of smaller storms to create larger ones. In the 1930s, 3 white ovals formed on Jupiter's surface, persisting for over 6 decades. During Galileo's mission, 2 of these ovals merged, creating a larger, more powerful storm. 2 years later, the 3rd oval merged as well, forming what scientists nicknamed Red Spot Jr. This newly formed storm, though smaller than the Great Red Spot, offered a unique opportunity to study the evolution of Jupiter's massive storms. Jupiter's storms are cannibalistic, swallowing smaller storms to grow larger. This food chain of atmospheric energy explains how the Great Red Spot became so massive. Thunderstorms act as primary energy harvesters, fueling the larger systems. However, this process doesn't explain why these storms persist for centuries when Earth's tornadoes and hurricanes dissipate within weeks. Jupiter's rapid rotation, completing a full spin in just 10 hours, may hold the key to its storm's longevity. Rapidly rotating systems like Jupiter's atmosphere create stable, long-lived vortices. Scientists demonstrated this concept using a rotating jar of water mixed with two dyes. Instead of chaos, the dyes formed two coherent vortices, mimicking the behavior of Jupiter's Great Red Spot. The planet's fast spin stabilizes its storms, preventing them from shredding themselves apart. The Galileo mission marked a turning point in our understanding of Jupiter, its atmosphere, and its role in the solar system. The mission's probe provided unprecedented data on the planet's chemical composition, challenging long-held theories about planetary formation. Observations of the Great Red Spot and other storms revealed a dynamic and enduring weather system fueled by internal energy and shaped by rapid rotation. As Juno continues its mission, it builds on Galileo's legacy, delving deeper into the mysteries of Jupiter. By studying its water content, magnetic fields, and core dynamics, Juno is poised to answer fundamental questions about the solar system's largest planet and its place in the cosmic story. Jupiter's storms, moons, and atmosphere serve as a reminder of the solar system's complexity and diversity. From the dry gaps encountered by Galileo's probe to the enduring legacy of the Great Red Spot, Jupiter captivates scientists and the public alike, offering a glimpse into the forces that shaped our cosmic neighborhood. Each new mission brings us closer to unraveling the secrets of this giant, illuminating the intricate dance of chemistry, physics, and time that governs our universe. Jupiter's swirling bands of red, white, and brown are among its most iconic features, but their origins remain puzzling. Scientists once believed these stripes represented rising and sinking gases, with warm air ascending to create bright zones and cooler air descending to form darker belts. However, data from Galileo challenged this assumption. Although Jupiter's atmosphere is hundreds of miles deep, only the uppermost layers are visible, where high-velocity winds blow in opposite directions. These winds drag the multicolored patterns across the surface, creating the planet's famous bands. The colored bands are associated with vertical motion, one researcher explains. But the rising motion may occur at one level, while sinking motion happens at a different depth within the same bands. To truly understand the mechanics of Jupiter's atmosphere, scientists will need data from Juno, which began its mission in 2011. Using advanced instruments, Juno is mapping Jupiter's atmosphere to depths of up to 350 miles, uncovering how the planet's rotation affects its layered structure. Is Jupiter spinning as a solid body beneath its visible clouds? Or does its interior behave like a swirling onion, with different layers rotating at varying speeds? Jupiter's rapid rotation not only shapes its storms, but also generates one of the most powerful magnetic fields in the solar system. Unlike Earth's magnetic field, which arises from the churning motion of molten iron in its core, Jupiter's field is born deep within its gaseous interior. Here, hydrogen is subjected to immense pressure, transforming into a metallic liquid capable of conducting electricity. This metallic hydrogen generates powerful electric currents, which create the planet's massive magnetic field. The sheer scale of Jupiter's magnetic field is astounding. It stretches over 50 times the diameter of the planet, extending far beyond Saturn's orbit. If it were visible from Earth, it would appear larger than the Moon in the night sky. This field traps charged particles and gases, forming intense radiation belts and fueling breathtaking auroras at Jupiter's poles. These auroras, caused by sulfur and other materials from Io's volcanic eruptions, being funneled into Jupiter's atmosphere, rival Earth's northern and southern lights in intensity. For the first time, Juno is flying through these charged particles to analyze the auroras and the magnetic fields that create them. By studying Jupiter's magnetosphere, scientists hope to gain a deeper understanding of the processes that sustain Earth's magnetic field and protect its atmosphere from the solar wind. While Jupiter's atmosphere and magnetic field are captivating, its moons offer equally compelling mysteries. Among the planet's 63 known moons, the four largest, Ganymede, Callisto, Io, and Europa, stand out as dynamic and intriguing worlds. These moons are locked in a precise orbital resonance, with Io completing 4 orbits for every 2 of Europa's and every 1 of Ganymede's. This cosmic dance generates tidal forces that profoundly affect their geology. Ganymede, the largest moon in the solar system, is so massive that it would be classified as a planet if it orbited the Sun. Its surface is a patchwork of craters, mountains, and frozen lava flows, hinting at a complex geological history. But what truly astonished scientists was Galileo's discovery that Ganymede has its own magnetic field, the only moon in the solar system known to possess one. This magnetic field suggests that Ganymede has a molten core, contradicting earlier theories that such a large moon would have cooled and solidified entirely over the solar system's 4-billion-year history. The discovery forced scientists to rethink their understanding of how moons and planets evolve. Adding to the intrigue, Galileo detected evidence of a second, varying magnetic field. This anomaly suggests the presence of a subterranean ocean buried beneath Ganymede's icy crust, a tantalizing possibility for the search for extraterrestrial life. Callisto, the outermost of Jupiter's 4 largest moons, presents a stark contrast to Ganymede. Its surface, heavily cratered and ancient, is the oldest landscape in the solar system. The moon's frigid surface temperature, around -279 degrees Fahrenheit, belies its potential internal complexity. Galileo detected a weak magnetic field around Callisto, raising the possibility of a subsurface ocean. However, data from Galileo's other instruments complicates this theory. Beneath its icy surface, Callisto appears to be a mixture of rock, ice, and metal, extending to its core. Unlike other moons, Callisto shows no signs of significant internal heating, challenging conventional theories of planetary formation. Scientists are left to puzzle over how a moon so cold and geologically inactive could harbor signs of liquid water. Io, the closest moon to Jupiter, is a world of fire and fury. Its surface is dotted with hundreds of active volcanoes, fueled by intense tidal heating from Jupiter's gravitational pull. This heating stretches and compresses Io's interior, generating the energy needed to drive its volcanic activity. Plumes of sulfur dioxide erupt from Io's surface, reaching hundreds of miles into space and contributing to Jupiter's auroras. Despite its hellish conditions, Io's volcanism provides valuable insights into the effects of tidal forces on celestial bodies. By studying Io, scientists hope to understand how similar processes might shape other moons and exoplanets. Of all Jupiter's moons, Europa holds the greatest promise for discovering extraterrestrial life. Beneath its smooth, icy surface lies a vast ocean of liquid water, kept warm by tidal heating. The cracks and ridges on Europa's surface suggest that the ice moves and shifts, hinting at active geological processes below. Future missions, like NASA's Europa Clipper, aim to explore this hidden ocean, searching for signs of habitability and life. If microbial life exists on Europa, it would profoundly reshape our understanding of biology and the potential for life beyond Earth. The Galileo mission transformed our understanding of Jupiter and its moons, revealing a dynamic system of worlds that challenge conventional wisdom about planetary formation and evolution. From the mysterious magnetic fields of Ganymede and Callisto to the fiery eruptions of Io and the hidden ocean of Europa, Jupiter's moons offer a wealth of scientific opportunities. As missions like Juno and Europa Clipper continue to explore the Jovian system, humanity edges closer to answering some of the most profound questions about our place in the cosmos. Is life unique to Earth? Or could it thrive in the icy oceans of Europa? Or the hidden depths of Ganymede? Jupiter and its moons hold the keys to these mysteries, promising to expand our understanding of the universe and our origins. Europa, one of Jupiter's most enigmatic moons, holds profound mysteries beneath its icy surface. Earlier missions depicted Europa as a pinkish-white world, marked with strange geological shapes and fewer meteor craters than expected. Scientists believe this scarcity of craters indicates that something on Europa is actively erasing them, perhaps water welling up from below the ice. Galileo's mission was initially planned for only 3 flybys of Europa, but compelling evidence about the moon's dynamic surface extended the mission. High-resolution imaging became a priority, as scientists aimed to understand how active Europa's surface truly is. Initially, they thought the resurfacing process might take billions of years. However, as each flyby returned data, estimates of the surface's age dropped dramatically, from billions to mere thousands of years, until they concluded that Europa might currently be geologically active. One of Galileo's most astonishing discoveries came while measuring Europa's magnetic field. The field shifts as the Moon orbits Jupiter, a phenomenon that suggests the presence of a conductive layer beneath the ice. Scientists realized there was only one plausible explanation. A vast, global ocean of liquid water lies beneath Europa's frozen crust. This ocean, estimated to be about 100 miles deep, could contain more liquid water than all of Earth's oceans combined. The revelation was groundbreaking, but it posed a new question. How could such an immense ocean remain liquid in the frigid conditions of space? Europa's surface temperature plunges as low as -200 degrees Fahrenheit, cold enough to freeze water solid. The answer, scientists believe, lies in the same tidal forces that drive volcanic activity on Io. Jupiter's immense gravitational pull stretches and compresses Europa as it orbits the gas giant, generating internal heat through friction. This heat keeps the subsurface ocean from freezing entirely, and also drives Europa's surface activity. Galileo's images revealed Europa's surface crisscrossed with bizarre ridges, often stretching for thousands of kilometers. These ridges, typically appearing in pairs with a central depression, baffled researchers at first. However, Laboratory experiments offered a plausible explanation. As Europa's icy shell is flexed by Jupiter's tidal forces, it bends and cracks. These cracks allow blocks of ice to slide back and forth, creating frictional heat. This heat warms the surrounding ice, causing it to rise and form the ridges visible on the surface. The ridges are just one sign of Europa's dynamic activity. Galileo also observed pits, domes, and flows of material on the surface, likely the result of ice volcanoes or geysers. Stains of red material streaking across the ice hint at salty deposits from the subsurface ocean, which may have seeped through cracks. These features suggest Europa is far from a static world. It is an active, ever-changing environment. The discoveries on Europa have profound implications for the search for extraterrestrial life. Beneath its icy crust, the subsurface ocean may host hydrothermal vents, similar to those found on Earth's ocean floors. On our planet, these vents support rich ecosystems, thriving on chemical energy rather than sunlight. Europa's hydrothermal vents, if they exist, could provide a similar environment for life to develop. Adding to the intrigue, Galileo detected carbon dioxide frozen on Europa's surface, likely originating from the ocean below. Carbon dioxide is a critical building block for life, and its presence suggests that the ocean might contain the necessary materials to support life. Astrobiologists are particularly excited by the possibility of microbial life. The combination of water, energy from tidal forces, and organic materials makes Europa one of the most promising candidates for life beyond Earth. As one researcher put it, where there's water, there's a very good chance there's life, especially if the materials to sustain life are present. On Europa, we seem to have both. Europa is not just a frozen moon, it is a world in constant motion. The tidal forces exerted by Jupiter continually reshape its surface and may even create currents within its subsurface ocean. This dynamic activity makes Europa a prime candidate for future exploration. NASA's upcoming Europa Clipper mission is designed to delve deeper into Europa's mysteries. Scheduled to launch in the 2020s, the spacecraft will carry advanced instruments to analyze the Moon's ice, search for signs of liquid water, and detect potential biosignatures. Scientists hope that Europa Clipper will answer lingering questions about the Moon's ocean and its potential to harbor life. While Europa's icy mysteries captivate scientists, Io, Europa's volcanic neighbor, presents an entirely different set of challenges. Slightly larger than Earth's moon, Io is the most volcanically active body in the solar system, with over 400 active volcanoes. Galileo's images revealed a surface constantly reshaped by massive eruptions, with lava flows and towering plumes of sulfur dioxide reaching hundreds of miles into space. Io's intense volcanic activity is driven by the same tidal forces that heat Europa's ocean. As Io orbits close to Jupiter, the planet's immense gravity stretches and compresses the Moon, generating heat through friction. This heat melts Io's interior, powering its volcanoes. The tidal forces also create dramatic tidal bulges, causing Io's surface to rise and fall by over 300 feet. This relentless stretching and pulling make Io a world unlike any other. Despite its hellish environment, Io provides valuable insights into the effects of tidal forces on celestial bodies. Understanding Io's volcanic activity could help scientists better understand similar processes on exoplanets and other moons. Galileo's exploration of Europa and Io underscores the diversity of worlds within the Jovian system. From the fiery eruptions of Io to the hidden ocean of Europa, Jupiter's moons challenge our understanding of planetary science and the potential for life in the universe. Europa, in particular, offers a tantalizing glimpse into the possibilities of alien ecosystems. If life exists beneath its icy crust, it would mark one of the most profound discoveries in human history. Such a finding would suggest that life is not unique to Earth, but could emerge wherever conditions are favorable. As missions like Europa Clipper and JUICE, Jupiter Icy Moons Explorer, continue to explore these fascinating moons, humanity edges closer to answering one of the greatest questions of all. Are we alone in the universe? Europa's icy depths may hold the key, waiting to reveal their secrets to those who dare to explore. The allure of discovering life beyond Earth drives scientists to focus their attention on Europa, one of Jupiter's most fascinating moons. Plans are in motion to return to this enigmatic world with the Europa Explorer mission, aiming to answer the monumental question, is there life on other worlds? This mission will provide vital data about Europa's icy surface, its structure, and the ocean hidden beneath. By surveying the moon's gravity, surface composition, and geology, scientists hope to better understand the tidal flexing that generates heat in Europa's interior and maintains its subsurface ocean. The Europa Explorer's radar system will be its most powerful tool, capable of creating a detailed 3D map of Europa's icy shell. This technology will reveal the thickness of the ice, the depth of the ocean below, and whether it spans the entire moon. Such data is essential for the next stage of exploration, breaking through the ice and exploring the ocean itself. Once we understand the ice's thickness, we can develop a plan to penetrate it and investigate the subsurface ocean, an endeavor that will likely redefine space exploration. While plans for Europa's exploration are still in development, groundbreaking technologies like endurance are already being tested here on Earth. In Antarctica, this advanced bionic submarine is exploring a lake buried beneath nearly 15 feet of ice, operating autonomously to navigate and gather data. This capability is critical for future missions to Europa, where communication delays would make real-time control from Earth impossible. Endurance represents a new breed of probes designed to function independently in extreme environments. Its work in Antarctica is preparing it for the challenges of Europa's icy crust, where a probe would need to melt its way through miles of ice. Such an endeavor would require a nuclear-powered heating system, capable of sustaining the intense energy demands for weeks or even months as it drills through the frozen barrier. Once beneath the ice, the probe would enter a vast ocean untouched for billions of years, searching for even the simplest forms of life. The discovery of microbial life beneath Europa's ice would be one of the greatest achievements in human history, says a researcher. And while we're likely to find microbes, the possibility of something more complex swimming in those waters cannot be ruled out. Finding even the simplest microorganisms in Europa's ocean would profoundly reshape humanity's understanding of life in the universe. If we discover life on Europa, it would strongly suggest that wherever water exists, life has the potential to emerge, a scientist explains. This realization could transform our perception of Earth's uniqueness and open new possibilities for life elsewhere in the cosmos. The search for life on Europa is about more than just microbes. It's about understanding the conditions that allow life to thrive. Europa's icy ocean could provide a template for identifying other habitable worlds within our solar system and beyond. It would also inspire hope that intelligent life may exist on worlds far beyond our own. As Europa inspires humanity to reach for new discoveries, another distant world captures our imagination: Pluto. Located billions of miles from Earth, Pluto is a tiny, icy object that defies expectations. With its dynamic atmosphere, suspected underground oceans, and potential for primitive life, Pluto challenges conventional ideas about where life could exist. Pluto's strange and captivating environment, coupled with its vast distance from the Sun, offers scientists a new lens through which to view Earth and our solar system. The exploration of Europa and the study of Pluto demonstrate that our quest for knowledge is far from over. These icy worlds hint at the incredible diversity of environments in the universe and hold the promise of answering some of humanity's most profound questions. Jupiter's magnetosphere is so vast that it stretches all the way to Saturn's orbit, influencing the environment of its neighboring planet. This magnetic field also interacts with Jupiter's moons, particularly Io, the closest of the 4 largest moons. Io's intense volcanic activity releases sulfur dioxide, which is drawn into Jupiter's magnetosphere and funneled toward its poles. The interaction creates breathtaking auroras, northern and southern lights, far more powerful than those seen on Earth. Juno's close passes through Jupiter's magnetic field allow scientists to analyze these auroras, providing valuable insights into the planet's dynamic processes. As remarkable as Jupiter itself is, its moons are equally compelling. Orbiting the gas giant are 63 moons, some of which are worlds unto themselves. The 4 largest, Ganymede, Callisto, Io, and Europa, are particularly intriguing, each presenting unique geological features and mysteries. These moons defy expectations, challenging assumptions about what moons should be. Ganymede, the largest moon in the solar system, is a world of mountains, valleys, craters, and frozen lava flows. If it orbited the Sun instead of Jupiter, it would be classified as a planet. Galileo's magnetometer revealed something extraordinary. Ganymede has its own magnetic field, the only moon in the solar system to possess one. This discovery was surprising because Ganymede should have cooled and solidified billions of years ago. Its magnetic field suggests the presence of a molten core, reshaping scientists' understanding of its evolution. Beneath Ganymede's rocky crust lies another surprise, a subsurface ocean of liquid water. This second, varying magnetic field detected by Galileo hinted at the presence of a conductive layer, likely a salty ocean hidden beneath the ice. The discovery of this ocean raises tantalizing questions about the potential for life in these hidden depths. Moving outward, Callisto, the most distant of Jupiter's 4 largest moons, offers a stark contrast to Ganymede. Its surface is ancient and heavily cratered, making it the oldest landscape in the solar system. Yet, Callisto remains geologically active, defying expectations for a small, cold moon. The reasons for its activity remain unclear, adding another layer of mystery to the Jovian system. Closer to Jupiter, Io is a volcanic powerhouse. Its surface is constantly reshaped by eruptions, fueled by the gravitational tug-of-war between Jupiter and its neighboring moons. Io's intense volcanic activity releases sulfur dioxide, creating a dynamic atmosphere and influencing Jupiter's magnetosphere. The bright plumes of sulfur and volcanic deposits give Io its distinctive, colorful appearance, earning it the nickname the Pizza Moon. Perhaps the most intriguing moon of all is Europa. Beneath its icy surface lies a vast ocean, potentially holding twice as much water as all of Earth's oceans combined. This subsurface ocean, kept warm by tidal forces, is one of the most promising locations in the search for extraterrestrial life. Europa's surface features suggest active geology, with cracks and ridges hinting at dynamic processes beneath the ice. NASA's upcoming Europa Clipper mission will explore this enigmatic moon, searching for signs of habitability and life. Jupiter and its moons represent a microcosm of the solar system's diversity and complexity. Each mission, from Galileo to Juno, has expanded our understanding of these alien worlds. Yet, the more we learn, the more questions arise. How did Jupiter form? What sustains its powerful storms and magnetic fields? Could life exist in the oceans of Europa or the depths of Ganymede? As Juno continues its mission, and new missions like Europa Clipper prepare to launch, humanity stands on the brink of answers that could reshape our understanding of the universe. Jupiter, with its storms, stripes, and magnetic might, remains a world of wonders, offering an endless source of discovery and inspiration. Through its exploration, we not only unlock the secrets of a distant giant, but also gain a deeper appreciation for the forces that shaped our own world and the cosmos beyond. Jupiter's moons are as enigmatic as the giant planet itself, each offering a distinct narrative of geological wonder and scientific intrigue. The Galileo mission transformed our understanding of these moons, revealing them as dynamic worlds, each shaped by forces both familiar and alien. Among the most remarkable are Callisto, Io, and Europa, moons that challenge conventional ideas about the solar system and may hold answers to the profound question of whether life exists beyond Earth. Callisto, the outermost of Jupiter's 4 largest moons, appears at first glance to be a cold and lifeless rock. Its surface, scarred by countless ancient meteorite impacts, is the oldest and most heavily cratered in the solar system. Yet beneath this rugged exterior lie mysteries that defy explanation. Pluto, long seen as a solitary enigma on the edge of the solar system, has proven to be a gateway to an even greater mystery: the Kuiper Belt. This vast expanse of icy objects extends billions of miles beyond Neptune, holding clues to the origins of our solar system. As technology improved and our understanding deepened, scientists realized that Pluto might not be an outlier, but part of a larger population of small, icy worlds that could redefine our understanding of the cosmos. The turning point in the search for the Kuiper Belt came in the late 20th century. In 1992, after years of meticulous observations, astronomers David Jewett and Jane Liu made a groundbreaking discovery: an object beyond Neptune that was not Pluto. The tiny icy body, known as 1992 QB1, was the first direct evidence of the Kuiper Belt's existence. Its discovery transformed Pluto's status in the solar system. No longer a misfit planet, Pluto was now seen as the largest known member of this distant belt of celestial debris. The Kuiper Belt is a remnant of the early solar system, a region filled with icy objects that never coalesced into full-fledged planets. Stretching from Neptune's orbit to nearly 50 astronomical units from the Sun, this region contains millions of small bodies made primarily of ice and rock. These objects are thought to be leftover building blocks from the formation of the solar system, preserved in their pristine state for over 4.5 billion years. The discovery of 1992 QB1 was just the beginning. In the years that followed, astronomers identified hundreds of other Kuiper Belt objects, KBOs, each adding to the puzzle of the outer solar system. Some of these objects are only a few miles across, while others, like Eris and Makemake, rival Pluto in size. Together, they form a diverse and dynamic population that challenges our definitions of planets and solar system structure. Pluto's reclassification as a dwarf planet in 2006 was a direct result of these discoveries. As scientists found more objects in the Kuiper Belt, it became clear that Pluto was not unique. Its size, composition, and orbit aligned more closely with the icy bodies of the Kuiper Belt than with the 8 major planets. The International Astronomical Union, IAU, established a new category for objects like Pluto, defining dwarf planets as celestial bodies that orbit the Sun, are spherical due to their own gravity, but have not cleared their orbits of other debris. This redefinition sparked a heated debate among scientists and the public alike. To many, Pluto's demotion felt like a loss. But to astronomers, it marked a leap forward in understanding the solar system's complexity. Pluto's reclassification placed it within a broader context, highlighting its role as a key to unlocking the secrets of the Kuiper Belt. In 2006, as Pluto's planetary status was being debated, NASA launched the New Horizons spacecraft. Its mission, to provide the first up-close look at Pluto and its moons and explore the Kuiper Belt beyond. Traveling at nearly 1 million miles per day, New Horizons reached Pluto in July 2015 after a 9-year journey. The images and data it sent back transformed our understanding of this distant world. Pluto's surface turned out to be far more complex than anyone had imagined. The spacecraft revealed vast plains of nitrogen ice, towering mountains made of water ice, and evidence of cryovolcanism. Geysers that spew ice and gas instead of molten rock. Pluto's atmosphere, thin and composed mainly of nitrogen, extends hundreds of miles into space. Charon, its largest moon, was equally surprising, with massive canyons and a dark polar cap. Perhaps most intriguing was the discovery of young geologically active surfaces on Pluto, suggesting that internal heat may still drive processes beneath its icy crust. This raised questions about the potential for subsurface oceans, not only on Pluto, but also on other Kuiper Belt objects. After its historic encounter with Pluto, New Horizons continued its journey into the Kuiper Belt. On January 1, 2019, it performed a close flyby of Arrokoth, a small, icy object located over 4 billion miles from the Sun. Arrokoth, with its flattened, two-lobed shape, offered a glimpse into the early solar system. Its surface showed no signs of significant collisions or reshaping, making it a time capsule of the processes that formed the solar system's building blocks. Arrokoth's simple structure suggested that it formed through the slow, gentle merging of smaller objects, a stark contrast to the violent collisions that shaped planets like Earth. This discovery supported the idea that Kuiper Belt objects are pristine relics of the solar system's infancy, providing crucial insights into how planets and other celestial bodies formed. The Kuiper Belt has not only reshaped our understanding of Pluto, but has also opened new avenues in planetary science. It serves as a bridge between the inner solar system and the distant Oort cloud, where long-period comets originate. By studying KBOs, scientists can trace the distribution of materials in the early solar system and understand the processes that shaped its evolution. The belt's diverse population also challenges existing models of planetary formation. Some KBOs, like Haumea, have elongated shapes and rapid rotations, suggesting dynamic histories involving collisions and gravitational interactions. Others, like Eris, are so far from the Sun that their surfaces remain frozen in time, preserving chemical compositions that may date back billions of years. As astronomers continue to explore the Kuiper Belt, they are also searching for signs of a true ninth planet. Some scientists hypothesize the existence of a massive unseen planet far beyond Pluto, whose gravitational influence could explain the unusual orbits of certain KBOs. This hypothetical Planet 9 could be 10 times the mass of Earth and orbit the Sun at a distance of hundreds of astronomical units. While no direct evidence has been found, the search continues, fueled by the tantalizing possibility of another major discovery. The exploration of Pluto and the Kuiper Belt represents a profound shift in our understanding of the solar system. These distant worlds, once considered peripheral, are now central to questions about planetary formation, the distribution of water and organic materials, and the potential for life beyond Earth. They remind us that the solar system is far more dynamic and diverse than we ever imagined. As new missions and technologies push the boundaries of exploration, the Kuiper Belt will continue to be a focal point for discovery. From Clyde Tombaugh's painstaking search in 1930 to the groundbreaking flybys of New Horizons, Pluto and its neighbors have captured humanity's imagination, offering a glimpse into the past and a gateway to the future. The story of Pluto is not just about one small world on the edge of the solar system, it's about the unending quest to understand our place in the universe. Pluto's story is one of discovery, reclassification, and enduring fascination. Once celebrated as the ninth planet of the solar system, it has become a symbol of the dynamic and evolving nature of planetary science. Though Pluto's status as a planet was stripped in 2006, its mysteries have only deepened, revealing an icy world with an extraordinary atmosphere, complex surface, and unique orbital behavior. The discovery of the Kuiper Belt in the 1990s transformed our understanding of Pluto. Astronomers realized it wasn't an outlier, but part of a vast region of icy bodies orbiting beyond Neptune. Clyde Tombaugh's 1930 discovery, once thought to be a singular planet, was reinterpreted as the largest known member of the Kuiper Belt. David Jewett and Jane Liu's detection of 1992 QB1 confirmed the existence of this region, and subsequent discoveries revealed thousands of similar objects, all relics from the early solar system. This new perspective reshaped how scientists categorized celestial bodies. Objects like Eris, discovered in 2005 and slightly larger than Pluto, challenged its planetary status. Eris's discovery underscored the need for a clear definition of what constitutes a planet. The International Astronomical Union, IAU, ultimately ruled that Pluto and similar objects did not meet the criteria for full planetary status, reclassifying them as dwarf planets. The IAU's decision was based on three criteria. A planet must orbit the Sun, have sufficient mass to achieve a spherical shape, and clear its orbit of other debris. Pluto failed the third requirement. Its orbit overlaps with objects in the Kuiper Belt, distinguishing it from the 8 major planets that dominate their orbital zones. While the reclassification was controversial, it highlighted the complexities of defining celestial bodies in a solar system that continues to surprise us. Despite this change, Pluto remains one of the most intriguing objects in our solar system. Its surface, atmosphere, and unique orbital properties make it a fascinating subject for study. For decades, astronomers speculated whether Pluto had an atmosphere. Given its vast distance, 3.2 billion miles from Earth, telescopic observations were insufficient to resolve the question. Even the Hubble Space Telescope, one of humanity's most powerful instruments, could only capture Pluto as a pixelated blur. The breakthrough came on June 9, 1988, when NASA's Kuiper Airborne Observatory conducted a high-altitude mission to observe a rare celestial event. Pluto was predicted to pass in front of a distant star, creating an occultation, a temporary dimming of the star's light as Pluto's shadow moved across it. This offered a unique opportunity to detect an atmosphere indirectly. Astronomers observed the star's light fading gradually rather than disappearing abruptly. This phenomenon, known as a central flash, indicated that Pluto's thin atmosphere was refracting the starlight. The atmosphere was confirmed to consist primarily of nitrogen, with traces of methane and carbon monoxide, similar to Earth's atmosphere, but vastly thinner and colder. Pluto's atmosphere is unlike any other in the solar system. Its tenuous gases are in constant flux, tied to the dwarf planet's eccentric orbit. Pluto follows an elongated path around the Sun, ranging from 2.7 billion miles to 4.6 billion miles in distance. This extreme orbit causes significant temperature variations, which in turn affect its atmosphere. When Pluto is closer to the Sun, its frozen surface sublimates, releasing gases into the atmosphere. As it moves farther away, these gases freeze back onto the surface, causing the atmosphere to collapse. This dynamic process means Pluto's atmosphere essentially breathes in and out over the course of its 248-year orbit. Recent studies suggest that Pluto's atmosphere is currently shrinking. Observations indicate that its nitrogen-rich gases are refreezing onto the surface as the dwarf planet moves away from the Sun. This phenomenon offers a rare glimpse into atmospheric processes on an icy world at the edge of the solar system. Pluto's surface is equally captivating. Covered in exotic ices, including frozen nitrogen, methane, and carbon monoxide, it presents a stark contrast to the rocky or gaseous surfaces of other celestial bodies. These ices create a reflective surface that makes Pluto one of the brightest objects in the Kuiper Belt. The surface is not static. Images from NASA's New Horizons mission in 2015 revealed a surprisingly dynamic landscape. Vast plains of nitrogen ice, towering mountains of water ice, and evidence of cryovolcanism, volcanoes that erupt with ice instead of molten rock, suggest ongoing geological activity. This discovery was unexpected, as small, distant bodies like Pluto were thought to be geologically inactive due to their lack of internal heat. Adding to Pluto's intrigue is its relationship with its largest moon, Charon. Discovered in 1978, Charon is about half the size of Pluto, making it the largest moon relative to its parent body in the solar system. Together, they form a binary system, with both bodies orbiting a shared center of gravity located outside Pluto itself. Charon's surface is starkly different from Pluto's, dominated by water ice rather than nitrogen and methane. Its massive canyons and fractures suggest a violent past, possibly involving subsurface oceans that froze and expanded, cracking the moon's crust. The dynamic interaction between Pluto and Charon has profound implications for our understanding of tidal forces, orbital dynamics, and the evolution of binary systems in the Kuiper Belt. NASA's New Horizons mission revolutionized our understanding of Pluto. After a 9-year journey, the spacecraft flew past the dwarf planet in July 2015. Capturing high-resolution images and collecting data that continue to reshape planetary science. It revealed a world far more complex than previously imagined, with evidence of glacial flows, atmospheric hazes, and potential subsurface oceans. The mission didn't stop at Pluto. New Horizons continued its journey into the Kuiper Belt, performing a close flyby of Arrokoth in 2019. This small, icy object provided a snapshot of the solar system's early history, offering clues about how planetesimals, the building blocks of planets, formed. Pluto's reclassification as a dwarf planet has not diminished its importance in planetary science. Instead, it has highlighted the richness of the Kuiper Belt and the need for continued exploration. Future missions aim to study Pluto and its neighbors in greater detail, searching for answers to fundamental questions about the origins of our solar system. Pluto remains a symbol of the ever-changing nature of scientific discovery. From Clyde Tombaugh's painstaking observations in 1930 to the groundbreaking findings of New Horizons, Pluto has continually challenged our perceptions of the cosmos. It reminds us that even the smallest, most distant worlds can hold the key to understanding our place in the universe. Pluto, a dwarf planet on the fringes of our solar system, continues to astonish scientists with its unique characteristics. Though shrouded in frigid temperatures and cloaked in exotic ices, Pluto exhibits surprising geological and atmospheric behaviors. Among its most intriguing features is its transient atmosphere, a fluctuating entity that hints at the dynamic nature of this distant world. Scientists are now uncovering clues that suggest Pluto may not be entirely frozen. Beneath its icy surface could lie a hidden ocean of liquid water. The discovery of Pluto's atmosphere came through a rare celestial event called an occultation, where Pluto passed in front of a distant star. The gradual dimming of the starlight confirmed the presence of a thin, tenuous atmosphere. Composed primarily of nitrogen, with traces of methane and carbon monoxide, Pluto's atmosphere shares chemical similarities with Earth's. However, it is so sparse that if compressed, it would form only a thin layer of frost or snow on the surface. What makes Pluto's atmosphere unique is its ability to vanish and reappear. Pluto's highly eccentric orbit takes it as close as 2.9 billion miles to the Sun and as far as 4.6 billion miles. As Pluto approaches the Sun, its surface ices sublimate into gases, creating an atmosphere. When it moves away, the gases refreeze, and the atmosphere collapses. No other known celestial body exhibits such radical atmospheric changes, making Pluto an exceptional case for planetary scientists. Pluto's atmosphere extends hundreds of miles above its surface, a phenomenon enabled by its weak gravity. This tenuous grip on its atmospheric gases means that they gradually escape into space. As Pluto gets closer to the Sun, this escape rate accelerates, resembling the behavior of a comet. Comets develop tails as their icy surfaces vaporize under solar heat. While Pluto lacks the dust of a comet's tail, it loses up to half a ton of atmospheric gases every second. Over billions of years, this has caused significant shrinkage of Pluto's overall mass and surface. Scientists estimate that up to 18 miles of Pluto's surface may have eroded into space over the solar system's history. This erosion, combined with its fluctuating atmosphere, has left Pluto's surface scarred by valleys, hills, and other terrain shaped by the interplay of heat, ice, and escaping gases. Infrared spectroscopy has provided insights into Pluto's surface composition, revealing a world dominated by exotic ices. Temperatures plunge to -396 degrees Fahrenheit, freezing nitrogen, methane, and carbon monoxide into solid forms. What we experience as breathable gases on Earth become Pluto's hills, plains, and surface rocks. Beneath this frozen crust lies a water ice mantle, forming the structural backbone of the dwarf planet. Pluto's landscape is anything but static. Observations from NASA's New Horizons mission in 2015 revealed dynamic glacial flows. Towering mountains made of water ice and regions shaped by cryovolcanism, volcanoes that erupt with icy slurries instead of molten rock. These findings challenge the notion that small, distant bodies like Pluto are geologically dead. As scientists delve deeper into Pluto's mysteries, they are considering the possibility of a subsurface ocean. Though surface temperatures hover around -390 degrees Fahrenheit, certain conditions might allow liquid water to exist beneath the ice. The key lies in ammonia, which acts as an antifreeze, significantly lowering the freezing point of water. Professor Bill McKinnon of Washington University in St. Louis has proposed that an ocean could persist beneath Pluto's icy crust. By mixing water with ammonia, the freezing point drops to nearly -142 degrees Fahrenheit, allowing water to remain liquid even in extreme cold. This concept mirrors what occurs in Earth's Arctic regions, where ice forms a thick crust over liquid water. However, maintaining a liquid ocean requires a heat source. Scientists believe that radioactive decay within Pluto's rocky core could generate enough heat to sustain such an ocean. Radioactive elements like uranium and thorium naturally emit heat as they decay, potentially warming the interior of the dwarf planet to critical temperatures. This internal heat, combined with the insulating properties of the overlying ice, could create an environment where ammonia-rich water remains in liquid form. The idea of a subsurface ocean on Pluto carries profound implications for our understanding of the Kuiper Belt and the solar system's formation. Many scientists believe that icy bodies like Pluto played a vital role in delivering water to Earth. During the chaotic early stages of planetary formation, collisions between comets, asteroids, and icy Kuiper Belt objects may have seeded Earth with the water necessary for life. If Pluto indeed harbors a liquid ocean, it raises the tantalizing possibility that such oceans may be common among icy worlds in the outer solar system. Subsurface oceans have already been proposed on moons like Europa and Enceladus, where tidal forces and internal heat sustain liquid water beneath icy crusts. The presence of liquid water, a key ingredient for life as we know it, expands the potential for habitability in the most unexpected places. Pluto's story is far from over. Its reclassification as a dwarf planet has not diminished its scientific significance. On the contrary, it has sparked renewed interest in the Kuiper Belt and the diverse range of objects that inhabit this distant region. Pluto serves as a window into the processes that shaped the early solar system and a reminder of the complexities that arise when exploring the unknown. Future missions may one day confirm the existence of a hidden ocean beneath Pluto's surface. For now, Pluto remains a frozen enigma, captivating scientists and the public alike with its extraordinary features. As we continue to unravel its secrets, Pluto challenges our understanding of what it means to be a planet and what it takes to sustain life. Pluto, once deemed the 9th planet and now classified as a dwarf planet, continues to captivate astronomers and the public alike. nestled in the remote reaches of our solar system, 3.2 billion miles from Earth. This icy world holds secrets that may unlock answers to fundamental questions about planetary formation, the origin of Earth's water, and the potential for dynamic processes even in the coldest corners of the cosmos. One of the most tantalizing theories about Pluto and its Kuiper Belt neighbors is their potential role in delivering water to Earth. Comets, rich in water ice, have long been proposed as carriers of Earth's oceans. However, astronomer Dave Jewett suggests that icy bodies like Pluto may also have played a part. These Kuiper Belt objects, numbering in the tens of thousands, range in size from small asteroids to massive ice balls over 600 miles across. Astronomers estimate that, in its prime, the Kuiper Belt was far more massive, up to 100 Earth masses of material compared to what remains today. Neptune's gravitational pull may have stirred this ancient region, dislodging icy bodies and sending them careening toward the inner solar system. Some of these fragments likely collided with Earth, potentially contributing to the formation of its oceans. If this theory holds true, objects like Pluto played a pivotal role in shaping life as we know it. Despite decades of observation, Pluto has remained largely an enigma. Even with advanced instruments like the Hubble Space Telescope, Pluto appears as a blurry, reddish ball of light. Efforts to map its surface have yielded intriguing, if limited, insights into its landscape. Infrared imaging reveals variations in surface brightness, suggesting a diverse and complex terrain. Astronomers believe Pluto's surface is composed of exotic ices, including nitrogen, methane, and carbon monoxide, frozen solid in temperatures nearing -270 degrees Celsius, 396 degrees Fahrenheit. These ices give Pluto its unique reflective properties, creating patches of light and dark that hint at plains, valleys, and potential cryovolcanic activity. For decades, Pluto remained the only major body in the solar system untouched by a spacecraft. That changed with the launch of NASA's New Horizons mission on January 19, 2006. The spacecraft, aboard an Atlas V rocket, embarked on an ambitious 9-year journey to the Kuiper Belt. Traveling at speeds exceeding 1 million miles a day, New Horizons aims to provide humanity's first close-up look at Pluto and its moons. The mission, costing $700 million, represents a milestone in space exploration. It marks a continuation of NASA's legacy of unveiling the secrets of the solar system, from the mountains of Mars to the methane lakes of Titan. For Pluto, the mission is especially poignant, as it seeks to transform our understanding of this distant world from a mere point of light into a dynamic, complex system. Clues about Pluto's surface and potential geological activity come from an unlikely source: Neptune's moon Triton. In 1989, Voyager 2's flyby of Triton revealed an icy world strikingly similar to Pluto in size and location within the solar system. Scientists speculate that Triton and Pluto share a common origin, with Triton possibly being a Kuiper Belt object captured by Neptune's gravity billions of years ago. Triton's surface features, impact craters, volcanic calderas, and active geysers, offer tantalizing hints of what might exist on Pluto. Voyager 2 captured images of Triton's geysers ejecting gas and dust up to 5 miles high, driven by the sun's distant but persistent warmth. Similar processes could be occurring on Pluto, where subsurface gases might escape through the icy crust in spectacular plumes. If Pluto possesses geysers, They could be driven by the sublimation of nitrogen and methane ices. As Pluto approaches the Sun during its elliptical orbit, solar energy may heat the surface just enough to turn solid ices into gas. These gases could accumulate in pockets beneath the surface, eventually bursting through as dramatic plumes. Such activity would provide further evidence of dynamic geological processes on Pluto. These processes may also involve cryovolcanism, volcanic activity that erupts with icy materials instead of molten rock. Understanding these phenomena could shed light on the internal structure and composition of Pluto, as well as its thermal history. New Horizons is equipped with state-of-the-art instruments to analyze Pluto's surface, atmosphere, and moons. Its camera system, tested on Jupiter and its volcanic moon Io during the spacecraft's slingshot maneuver, is capable of capturing detailed images and data that were previously unimaginable. By the time it reaches Pluto in 2015, New Horizons will have traveled nearly 3 billion miles, crossing vast stretches of empty space to reach its distant target. The mission's primary goal is to map Pluto's surface in unprecedented detail, revealing features that have remained hidden from Earth-based telescopes. It will also study Pluto's atmosphere, examining how it behaves as the planet moves away from the Sun, and its gases refreeze onto the surface. Additionally, New Horizons will investigate Pluto's moons, particularly Charon, whose gravitational interaction with Pluto creates a unique binary system. After its primary mission at Pluto, New Horizons will continue its journey into the Kuiper Belt, exploring other icy objects that hold clues to the early solar system. These objects, remnants from the time of planetary formation, are thought to contain pristine material that has remained largely unchanged for billions of years. By studying these distant worlds, scientists hope to piece together the story of how the solar system evolved. The Kuiper Belt, once thought to be a barren region, is now recognized as a dynamic and diverse area filled with potential discoveries. As New Horizons races toward its destination, anticipation builds for the moment when humanity will finally see Pluto up close. The mission promises to answer long-standing questions about the dwarf planet and its role in the broader context of the solar system. For astronomers and space enthusiasts, New Horizons represents not just a scientific endeavor, but a journey into the unknown. A bold step toward understanding the outer reaches of our cosmic neighborhood. Pluto, long a symbol of mystery and isolation, is poised to reveal its secrets. Whether it's the confirmation of geysers, the discovery of subsurface oceans, or the unveiling of a complex and varied landscape, Pluto's story is far from over. As New Horizons approaches, we stand on the cusp of a new era in our exploration of the solar system. One that promises to deepen our understanding of the universe and our place within it. The New Horizons mission represents one of the most ambitious endeavors in space exploration. A high-speed voyage to the outer reaches of the solar system to unlock the secrets of Pluto and its mysterious Kuiper Belt neighbors. Launched as the fastest spacecraft in history, New Horizons races through the cosmos at an astonishing pace. But this speed comes with a trade-off. The spacecraft has only a fleeting moment to observe Pluto up close before it speeds past and delves deeper into the icy expanse of the Kuiper Belt. In July 2015, after a 9-year journey across more than 3 billion miles, New Horizons will approach Pluto, providing humanity with its first detailed look at the enigmatic dwarf planet. As the spacecraft nears its target, the resolution of its images will far surpass that of the Hubble Space Telescope, allowing scientists to study features on Pluto's surface as small as a football field. However, the critical window for capturing the highest resolution data lasts just a day and a half, an intense period of observation requiring perfect coordination and precision. The mission team has spent years preparing for this fleeting encounter. Over the course of its journey, New Horizons has been periodically awakened from hibernation to ensure its instruments remain in peak condition. Each year, the spacecraft undergoes rigorous testing, observations of celestial objects, and system calibrations to guarantee it will be ready for its ultimate mission: to reveal Pluto's secrets and answer profound questions about the formation of the solar system. One of the mission's key objectives is to investigate the role of Kuiper Belt objects, like Pluto, in delivering water and organic materials to the inner solar system, processes that may have been crucial to the emergence of life on Earth. But the team knows that the greatest discoveries may be those they cannot yet predict. The most exciting things we'll learn, one scientist notes, are the things we didn't even know to ask. The anticipation surrounding New Horizons is immense. For decades, Pluto has been a symbol of the unknown, a frozen frontier on the edge of the solar system. With its eccentric orbit, exotic ices, and potential underground oceans, Pluto challenges our understanding of planetary science. Could it harbor geysers driven by subsurface gases? Could ammonia-laced water flow beneath its icy crust? Could there even be primitive forms of life? Adding a poetic touch to this historic mission, New Horizons carries the ashes of Clyde Tombaugh, the astronomer who discovered Pluto in 1930. His journey, begun with a 12-inch telescope in Arizona, now extends to the farthest reaches of the solar system, a tribute to the enduring spirit of exploration. When New Horizons reaches Pluto, it will mark not only a scientific milestone, but also a testament to human curiosity and ingenuity. From its humble beginnings as the 9th planet to its reclassification as a dwarf planet, Pluto's story has been full of surprises. With New Horizons, we are poised to uncover the next chapter in its saga, bringing us closer to understanding our place in the cosmos. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.